Okay, so I've gotten a number of questions about how to deal with reflecting things across a transformer. So let me try to address that because that's a question on the homework and it's one that we've dealt with before. All right, so let's say I've got this set up. So here's a source Vs. Let's say there's some impedance in series with it. And then it's hooked up to some sort of an ideal transformer. Okay. 2, 3. All right. And so on the secondary of this ideal transformer is some impedance Z2. Okay. I've got N1 turns here and 2 turns here. All right. And let's call this V1. Let's call this V2. Call that current I2. Okay. And call that current I1. All right, so our goal is to reflect this over to here. Now let's think for a second about what a transformer is really doing and seeing if that helps us to understand what the idea of this mapping, this reflection is. Okay, so here's the picture of a transformer. Okay, I've got a coil here, and I've got a coil over here. Okay, so let's say I had that Z line and Vs hooked up right there. Key thing to ask yourself is, in this setup with an open circuit on the secondary, this would be I1. How much current flows into there? All right, well the short answer is none. Okay, why not? Okay, well when we described the ideal transformer, one of the things we said was that the impedance of this thing is infinite. Right? We said that the permeability of this magnetic material is really, really high. If that permeability is really high, then the primary inductance, right, the inductance of this coil is essentially infinite. Okay? And so there is no current flow through this setup. The only time current actually flows into this coil is if what's happening is the energy that flows out of this source goes into a field that couples over here, and then energy begins to flow over here. Okay? We said we thought about the secondary as sort of another circuit, right? And that other circuit could be thought of as a voltage source, all right? And if there's a load connected to it, then there's some energy coming out of this source. If I don't have a load on this secondary, right, if it's open circuit, then there is no energy being transferred over to here, which means no current needs to flow into this thing. Only at the point at which energy is coming out of this source, getting transferred over to the secondary coil and into this load, is that the time, only then, that I1 actually is non-zero, right? Essentially, there is infinite inductance here so that no current will flow. All right, the way that we ultimately end up kind of modeling a transformer, as you'll see, a real transformer, is to say that there are two reasons why current can go into this into the primary. One is because there is energy transfer over here, and the other is because there's essentially a parallel path where current can go into what we call the self-inductance. In our ideal transformer, there is no current that can flow on this side as a result of the coil itself. The only reason why energy can flow or current can flow into this primary is because it is there to transfer energy to the secondary. Okay? So if I didn't have this here, there would be no current flowing here. All right? So there's an intricate relationship between what the voltage and current here are at the primary and what they are at the secondary. The idea of the reflected impedance idea is to say, well, there must be some way to effectively represent the action of this impedance over here, because it is this impedance that is completing this circuit. In other words, with nothing here, if that's an open circuit on the secondary, This is an open circuit here across the primary. No current flows into it. So there must be some way to move that secondary side impedance over to the other side so it effectively completes the circuit there. Okay? And there is. All right? So here's how we do it. If I look at that picture right here, I can say that V2 equals I2 Z2. All right? That's basically an Ohm's law statement looking at that side of the transformer. Okay? So V2 over I2 is equal to Z2. Okay? Got that. Now, what do I know? I also know that V1 over N1 equals V2 over N2. Similarly, I know that N1 I1 equals N2 I2, okay, for the setup that I've got there. So I can rearrange this as V1 equals V2 times N1 over N2, and I1 equals N2 over N1 times I2, okay? And then, okay, what do I know? I've now represented V1 in terms of V2. I've now represented I1 in terms of I2. So what I want to do is somehow combine these things to say, well, what kind of an impedance could I put here that would relate this voltage and this current? Okay. Well, to do that, I can basically say, well, that impedance would be Z1. And that impedance is like that. V1 over I1 is an impedance, as units of an impedance. And it's basically some impedance that created this relationship between voltage and current. All right, so I do that by taking the ratio of those two things. Well, that becomes basically V2 over, well, let me do it this way, V2 N1 over N2 divided by I2 N2 over N1, which is V2 over I2 times N1 over N2 quantity squared. Okay? The important thing about what I just did right there, okay, the important thing about what I just did right there is this can be represented now as Z2 times N1 over N2 quantity squared. All right? Basically, we're saying that the voltage and current here, okay, can be represented by some impact of what this impedance is doing. So in other words, this circuit could effectively be redrawn as this. Okay. Could be redrawn as that. Okay. Where if I think about it, right here, I have V1. Right here, I have I1. In other words, this circuit, these two circuits are functionally the same. From the perspective of this source, right? This source, if I do KVL around this loop, I have Vs equals I1 times Z line plus V1. Okay? I still have the same thing here. Vs equals I1 times Z line. So this is Z line. Vs equals I1 times Z line plus V1. It's the same thing. Okay? This impedance right here is that impedance I just defined, Z1, which is the reflected, sorry, it's N1 divided by N2 squared. Okay? That's the crucial thing, right? What I'm doing is saying, because I recognize the fact that the only reason current flows in the primary is because there's a load on the secondary, all right? That effectively what I should do is I should be able to tell myself, how do I move this current over to here and try to essentially try to say, what impedance could I replace the transformer with that represents that energy transfer over to the secondary? All it is essentially saying, if I analyze the circuit with just the voltage and current relationship, there's effectively two steps here. Like imagine I asked you, what's I1? Well, if I asked you what I1 was, you'd have to solve for what's going on over here, right? And then you'd have to map the voltages over. You have to figure out the current relationship. This basically combines the voltage and current relationship into one step, okay? So effectively, it's the exact same analysis, but it's basically saying, all right, because the secondary loads the primary, all right, it's like saying this is an open circuit until I put a load over here. Once I put a load over here, the current that flows into this guy is controlled by what the load is over here. So there must be some way of re-representing everything at this point based on this guy himself. And that's exactly what we're doing. We're saying, all right, give me some equivalent impedance that I can put right here that models the energy transfer over to there. That's all it is. All right. If you're not comfortable with it, that's okay. Right. Eventually you'll become comfortable with it. Right. But it's probably fair enough to say if you can understand the voltage current relationships here, you're probably good enough. All right. But this idea of reflected impedance essentially makes our analysis one step easier.